Welcome back to Chapter 7. Let's pick up here with our next topic, which is aqueous solutions and solubility. So because water is so pervasive and so many things will dissolve in water, reactions that take place in water are very, very common. And as a matter of fact, I would say at least half of the reactions that we do in the average chemistry lab, so that includes principles of chemistry, general chemistry, organic chemistry, probably close to half of those, if not more than half, are what we would term aqueous chemical reactions, in that they take place in water. Now, some molecules, when they dissolve in water, undergo a special process that we call dissociation. And this specifically happens mostly with salts. There are some other molecules that do this as well, acids and bases, for example, but we're not going to get into those here. But salts especially tend to dissociate in water. And what I mean by dissociate is that they break apart. They break apart into their individual components. So, for example, sodium chloride, NaCl, when you put it into water, it does not stay as NaCl. Instead, what happens is the crystal lattice of the sodium chloride gets broken apart, and the individual ions actually get dissolved into the water and carried around by the water molecules. So you don't have, a big lattice of, just one atom on top of another, on top of another, on top of another, which is what you would normally see inside of a solid crystal lattice like that. Instead, these are just broken apart, and you just have individual ions floating around in solution. So we have sodium chloride there that breaks apart, it dissociates in solution. We also have another molecule here, which is silver nitrate. This is another salt, and we know, and by the way, when I say salt, I don't mean just like table salt. Scientifically speaking, a salt can refer to any molecule that is an ionic molecule, so any molecule that has a metal and a nonmetal. You can call that a salt. So this is a salt because we have silver, which is a metal, and then the nitrate ion, which is made up of nonmetals. And this is also going to dissolve in water and dissociate. The silver and the nitrate ions break apart from each other, and they are individually dissolved in the water, so it dissociates. But if you take the silver from this molecule that dissociated and the chloride from this one that dissociated, put them together to get silver chloride, silver 1 chloride specifically, this actually does not dissolve in water. This will not dissociate. So why is that? Why is it that in this molecule it dissolves and in this one it dissolves, but over here it doesn't? Well, this leads us to the main topic here for this video, which is the solubility rules. So the solubility rules determine what molecules are going to be soluble and what molecules are not going to be soluble. And these are based on the individual ions in the solution. So every individual ion, every individual cation and anion is more or less likely to dissolve in solution. And because you always have two, you always have to have a cation and an anion, because you always have the two, you have to take both of those into account. Because you can't just say, oh, well, we have this anion, it really likes to dissolve, so therefore the molecule is going to dissolve. There are a few rare cases where we can do that. But for the most part, we can't just look at one of the ions and say it's definitely going to dissolve or it's definitely not going to dissolve. Instead, we have to look at both. We have to consider both of them. And that's what was going on back here. The chloride and the silver in different molecules dissolved because they were paired up with things that helped them dissolve. But then over here, when you put them together, the combination of silver and chloride were not soluble. They would not dissociate in water. They wouldn't dissolve into the water. So there's no easy way to know exactly which compounds are going to be soluble and which ones are insoluble. What we know today is mainly just because people went out there and just actually looked at it and just put some stuff in water and saw if it dissolved or not. Like I said, there are some ions that are always going to be soluble, but those are rare. Those, I think there's maybe 5 of them, 5 or 6 different ions that will always dissolve in water no matter what you pair them with. But there is a whole lot more than 5 ions out there. Most things, it is going to depend on what it is paired with. So, this flowchart comes from your book, and if this flowchart makes sense to you, use this flowchart. I don't really like this very much, though. I think this is really busy, and it's kind of hard to tell what's going on. Obviously, I can read it just fine. I can tell what's going on just because I'm very experienced with these things, and most of the time I don't even need to look at a solubility chart because I've been doing it so long I just know. But for someone that's new to this, this is kind of a lot all at once. I actually prefer this. Now I know this isn't super calm either, like there's a good bit of stuff going on here too, but I think this is a little bit more clear as to what's going on. So these solubility rules, or this solubility table, what this is going to allow us to do is to figure out if a molecule will dissolve in water or not. Specifically, if a ionic molecule will dissolve in water or not. And remember, if it dissolves, it's dissolving because it's dissociating. Ionic molecules do not dissolve if they're not dissociating. So these will dissociate in water if they're dissolving. So everything in this top section here, these ions, are commonly soluble. They are usually soluble. They will usually dissolve in water. And the exceptions to that rule are listed to the right. So notice here that 2 of these don't have any exceptions listed. So nitrate and acetate, no matter what you pair them with, they will dissolve in water. So if you remember, I mentioned there were a few that were like this. These are 2 of those. These 2, no matter what you put them with, it will dissolve in water. These 4, most of the time, will dissolve in water, but the exceptions to those are listed here. So chloride, if you remember, we had sodium chloride that dissolved. Chloride is generally soluble, but one of the exceptions to that is silver. And that is why, back here, this is insoluble. Because we paired up the molecule that's normally soluble with an exception to that. So if silver and chloride are together, they will not dissolve. And so you can see the rest of these have mostly the same exceptions. So lead and mercury really don't like to dissolve, and silver is kind of, sometimes it doesn't want to and sometimes it's fine dissolving. But these on the top here are generally soluble. The ones on the bottom are generally insoluble. So sulfide, carbonate, phosphate, and hydroxide are usually not going to dissolve, but there's a few more exceptions here than we had with the ones that are generally soluble. So ammonia is an exception for all of these, as is all of the alkali metals. And remember, the alkali metals are the lithium, sodium, why is it doing that to me? Lithium, sodium, potassium, and so on down the line there. But these are the 3 most common ones you'll come across: lithium, sodium, potassium. So that's these alkali metals. So those are exceptions to these not dissolving. So essentially those want to dissolve enough that they can force these things to dissolve. And then there's a few other exceptions for these. So the sulfide has a few extra exceptions, and the hydroxide has a few extra exceptions. But the main exceptions there are ammonium and the alkali metals. So when we are trying to determine if a molecule will dissolve in water or not, we're just going to go to this table, find the anion in the molecule, see if it's one that is generally soluble or generally insoluble, and then check to make sure that it's not paired up with an exception. Now, you do not have to memorize these solubility rules. So, hallelujah for that. No need to memorize those. I'm going to give you a copy of that flowchart to use on any exam that you might do. And obviously, if you're just doing homework at home, you can just look it up in the book or in the slides here. The only thing you need to do is you need to know how to use those rules. So, let's go ahead and look at a few examples here. So this is asking us to determine whether each of these compounds is soluble or insoluble in water. So the first one here is silver bromide. And if we go back to here, bromide is generally soluble. Remember, we're always going to look for the anion first. So bromide is generally soluble, but silver is an exception. Silver is an exception to that. So what that means is this is going to be insoluble. So that is not going to dissolve in water. Calcium chloride. So chloride is our anion. Chloride is generally soluble, and calcium is not an exception to that. So that means that we are going to have soluble here as our answer. Calcium chloride will dissolve in water. Lead nitrate is the next one. This one, I don't even have to go back and look at the table. I remember that nitrate is one of the anions that is always soluble, and there were no exceptions. So this is going to be soluble. And then the last one here, lead sulfate. Sulfate is generally soluble, but lead is an exception to that. So because we have an exception to the rule, this is going to be insoluble. That will not dissolve in water. And if I remember correctly, this is actually a very vibrant yellow color. I think that is or maybe that's lead iodide. Well, anyway, it is not soluble in water. Real quick here, I want to point out the different what's in these beakers here. This comes from, I believe this comes from Conceptual Checkpoint 7.4. So if I look that up real quickly here, so I have my book handy. So Conceptual Checkpoint 7.4 says, which image best depicts a mixture of barium chloride and water? So if we have barium chloride, is it going to look like this, or like this? I can tell you right off the bat, it's not this one. Because barium chloride doesn't exist in chunks like that, unless we happen to put this barium chloride in a blender before we put it into the solution. So it's either going to be this one or this one, depending on if it is soluble or not. So if we go back and check, it was barium chloride. Chloride is generally soluble, and barium is not an exception to that. So this is what that solution would look like. The barium and the chloride would dissolve, and it will dissociate, and get carried around in the solution by the water. It would not be a solid sitting at the bottom. Alright, so I think we'll call it there for this video. In the next one, we're going to look at what happens when a reaction forms an insoluble compound. What happens if we take two different liquids that individually are soluble, but when you put them together, they form an insoluble compound. That is what we call a precipitation. So we're going to look at that in the next video.